The best thing about calculating flux through a surface, so these are surface integrals of vector valued functions, is that there's this like ugly d sigma thing at the end of every surface integrals, and you always got to like find a magnitude and then divide by the magnitude. So what I'm saying is that there's this like wait for it, there's this like cool thing where it like all cancels out, and somehow the surface integral of a vector valued function actually ends up being a little bit easier in a way to calculate than surface integrals of a scalar valued function. I may be dating myself here, and I don't know when you're watching this video. It could be like 1,000 years in the future, and you have no knowledge of this guy. But there used to be a TV show called Mythbusters, and this guy's name is Adam Savage. Anyways, he built this like ridiculous modified Nerf blaster, and it shoots 1,000 rounds. And in our thought experiment here, we're going to imagine Adam shooting his Nerf blaster at a wall, and we're going to suppose that he shoots all 1,000 rounds in 1 minute. In the first scenario, Adam is shooting the Nerf rounds, and he is facing straight perpendicular to it, so that the Nerf rounds are like basically pointing straight at the surface. And then in the second one, the surface has been tilted, so he's kind of shooting at it at an angle. So just take a minute and imagine what would happen in both those scenarios. Right, so he's just blasting away, and there's a little bit of spread because this thing is like super powered. So let's suppose that the spread happens in like a circle there on the board, and these little Nerf rounds are gonna hit at 1,000 different places. Maybe I'll use little dots, and they hit like at 1,000 different places inside his little spread there, okay? And then in the second situation, here's the crucial thought. Because he's kind of at an angle, that means that the spread will kind of get elongated out like that. So this means that the Nerf rounds will be hitting over a larger area. Remember, it is the same total number of rounds and the same total amount of time, but the first situation where he is directly perpendicular, this is all the total spread. This has a small spread, and in the second one, there's going to be a larger spread. What I want you to think about is what would be the density of the rounds striking against this surface. So in the first situation, remember, both of these things, it's the same total number of rounds that collide with the like surface here. And in the first situation, they're in a smaller area, and in the second situation, they're in a larger area. So what that means is that this first situation, the density must be very large, right? You're trying to pack a lot of Nerf rounds into a small area. And in the second situation, there must be less density because you're packing the same amount of rounds into a larger area. So the most dense sort of collisions that Adam Savage can have with the board is when he is straight up perpendicular to the board in the same direction as the normal vector. And the more at an angle that he gets with the normal vector, the less and less density there will be. But that's exactly what projections do. When two things are pointing in the same direction, projections give you the largest value, and each little angle each little bit that you increase the angle makes the projection smaller, right? Like, so if here is the normal vector, okay, this is the largest possible projection that I can produce, okay? But every little angle that I transform this by, right? Every little angle, as I'm turning this angle, that's going to make the projection smaller. The more and more and more that you turn this, the force field, the smaller and smaller and smaller the projection's going to get. So what that means is that the flux density is the projection of the velocity onto the vectors that are normal to the surface. Okay. Now, if you have a surface and it's kind of curvy and you have a bunch of particles that are passing through the surface, what you need to do is chop the surface up into a bunch of little pieces. Each of those little pieces we're going to call d sigma. Now, the particles per unit area, that's what we calculate when we calculate flux density. Those are the units of the flux density. So If you multiply that by an area, you're going to get the total number of particles that are passing through one little patch. So now what we need to do is add up all of the particles that are passing through each little patch. If we add all of those up, that is going to give us the total number of particles that are passing across the surface. And that's what we call the flux. In this example that we just did, I mean, this seems a bit silly because we already knew the total flux. The total flux was 1,000 rounds per minute. So what we were really doing was we had all those we had all those particles and we were chopping it up into a little piece, and then we were finding the total number of dots in each piece and then adding them all up. So the point of this is, if you didn't know what this number was, then this is the math that you would have to do in order to figure it out. Okay, I love this part. You guys are gonna love this. All right, so all right, now we're just gonna go into a bunch of stuff we've seen before. If you haven't seen it, it should be linked somewhere on the screen. The video where I do this last time. You got a surface, you chop it up into a bunch of little pieces, you got a parameterization, and then we've already constructed this expression. That's going to be the area of this little patch right here. Well, I guess so this would be r sub u du and r sub v dv, and then this d sigma is going to be the area of that little patch right there. All right, so check this out. If I'm saying we got this piece, now we need to calculate that n hat right there. So one thing you can do is, so I got r sub u there and r sub v there, they're on the surface, so there is going to be some kind of normal vector. So I can just right-hand rule, if it wants to go out or in. You got to be careful about whether or not you're calculating the outward normal vector or the inward normal vector. So in this case, how's my right-hand rule? This time it would be r sub u, r sub v. That would give me the one going up as I've drawn it here. So r sub u cross r sub v, that's going to give me a normal vector. But the issue is this may not be a unit vector. Remember, when you're calculating projections, you do the dot product with a unit vector. So I need to make this a unit vector. So n hat is going to be just whatever n is, and then I'm going to find its magnitude and then divide by that. So n hat is going to be r sub u cross r sub v. This is a vector, divided by the magnitude of r sub u cross r sub v. Okay, can anybody see what's going to happen? And look, at the end of our calculation here is n hat d sigma, and look at what is happening in the denominators of our n hat and our d sigma. It's canceling out, OMG. So I'm just literally plugging things into the formula. So f right here goes with f right there. N right here goes with what we calculate. Well, n hat goes for what we calculated for n hat. And d sigma right there goes with what we already have for d sigma. So that means that these two magnitudes right there are going to cancel. Okay, so that's it. Now we get the final formula for total flux, which is the double integral of f dot r sub u cross r sub v du dv. So there is implied parentheses right here. And this is, you're integrating over all the values of the parameter. So this is the final formula that we're going to use to calculate the total flux through a surface. That was fantastic, but we got to do an example here. We're going to lose our minds. I picked an example here that is really simple, deliberately. What I'm trying to do is, we're going to do this r sub u cross r sub v in order to calculate a normal vector. But this specific problem, we actually don't need to go through all that business because this is just the equation of a plane. So you can actually always just read off a vector that is normal to the plane. Another way you can see this, if you want to think of it this way, is this is a level curve of a higher dimensional function. So if I want to, I can just calculate the gradient of this surface, well, the gradient of this level curve, and that will give me a normal vector. So I'm going to get n equals, so 3, 2, 1 here as the normal vector. I just want to point out about this problem that we are trying to calculate the flux upward through this surface. This is like a kind of a triangle. I should also put, I just mean the portion of this that is in the first octant. I didn't write that down. I'll fix it. But what I'm saying is that we just want to make sure that it says upward in the problem. So I just want to make sure that I am actually calculating a vector that points up. But I'm just saying, like, all these coordinates are positive, especially like the z coordinate, right? So you're going to go over and then up some amount. So this is always going to be a upward normal vector. So there it is. You know, you can actually see through this problem, but let me do it the parameterization way just so we can check and make sure all this like sort of checks out and makes sense. It's always easy to parameterize surfaces when the functions are defined explicitly. We can just do our kind of trivial parameterization. So chosen the letters U and V here. And I drew a quick little sketch of the portion of the surface that's in the first octant. So we're gonna have to use the right-hand rule to figure out which cross product we want to do. So let's suppose that we're at a point right here, and I want to find out which direction does r sub u point. So we're going to move along the surface, and r sub u is going to be which direction you point if you tried to increase the u value or you tried to increase the x value. So if I try to increase the x, that means I'm going to go down the x-axis that way. So that means r sub u is going to point in that direction. And likewise, if I tried to increase the y value, then r sub v is going to point in that direction. So I need to do u and then v. Let me draw the hand. Okay, there's my best hand. What I'm saying is that according to this setup, n is supposed to be pointing upward through the surface, and I've done it there, right? R sub u cross R sub v does produce a normal vector. Aha, so now I just need to start calculating. So partial derivatives. So partial derivatives are easy. So here's my surface, and I need to calculate the u partial derivative. So I did the partial derivative of u and I got 1, the u partial derivative of v and I got 0, and then the u partial derivative of z and I got -3, and then r sub v is the same way. So next up is a cross product. Okay, and this is totally working. So in the most basic case that your surface is a plane, you can just read off the normal vector. But I just want to point out that if you do this the parameterization way, it does actually give you the same answer as if, you know, you just kind of use pure reason. So, you know, in general, this is going to be our method. There are some shortcuts, but what I'm saying is that like the parameterization method, it just always works. So here is an example of it working. Okay, we are so close to being done. Now, the formula is F dot r sub u cross r sub v. So finally, we are bringing the velocity field into play here. So this says xy. X is u, y is v. So this right here is xy. Then 3x, x is u, so here I have 3u. Okay, and then y plus z. So y is v, so there's y plus z, and there's z right there. So now basically what I'm saying is that you need to take the parameterization and plug that back into the force field, the velocity field. Now this should be dot product with r sub u cross r sub v. So there it is. That's what we calculated, dot product with r sub u cross r sub v. So I need to find out the limits of integration, and I need to actually work out this dot product. Let me do that. For the limits of integration, what we need to do is pick all of the u and v values that give us points on the surface. So you can see this shadow right here in the xy plane is all of the u and v values that give us points on this surface. So that shadow happens when z equals 0. So I just plugged z equals 0 into this equation, and it got me this. So this is basically just like our usual setup and integral trick here. So now I guess I'll use the laser beam method. So if I, what do we want to do? dv first. What do I do? du first down here, so I'll do du first. So if I go this way, then this laser beam enters the region at u equals 0, and it exits the region. So this is 3x plus 2y, so that's 3u plus 2v equals 6. And what am I trying to solve for u here? So this means u is going to be 2 minus 2/3 v. I just solved that, so that's that little exit point right there. So u equals 2 minus 2/3 v. And then these are all these v values right there. So when u equals 0, v will be 3. So this is going to be from v equals 0 up to v equals 3. That's it. So now I just need to do this dot product and do this double integral, and we are done. So let me just work this dot product out right here. This is really easy, right? I can just multiply and add them up. So I get on the inside here, it's going to be 3uv plus 2 times 3u, right? I'm just like doing this one times this one and this one times this one. So 3uv plus 2 times 3u plus 1 times v plus 6 minus 3u minus 2v. So that's it. That's it. We finally have a double integral set up in terms of u and v. So you just power rule your way through this, and that is going to spit out the total flux. So this was a really simple example. This is not all the possible ways that this can play out. There's a lot of nuance to this, especially in this part right here where you have to choose the parameterization of a surface. But this video is already like 7 hours long. So congratulations for making it till the end. I'll make another video where I just start with this formula and I work out some more examples. Please let me know if you have questions. I understand that this is complicated.